Today, we are introducing you to our all new game changer release of Apex. That's Apex Iberian Lynx, and shortly we call it as Apex IL. We also would like to show you how it is best suited for aerospace industry. So why we believe it is best suited for aerospace industry? First of all, it will allow you to improve your productivity at least 10 times, if not more, in modeling, simulation, using Nastran and post-processing, the whole 9 yards of the CAE. It is, has always been, an enjoyable experience, and it will continue to be that way even in Apex Iberian Lynx. And it is not only for analysts, it's also for non-specialists and beginners, and also targeting the design engineers who can do the what if scenarios within Apex. And it is a flexible licensing environment. That means what we have had in our previous releases in the structures module, we migrated all those functionalities into modeler. That being said, Apex Modeler is truly a pre and post processor. Although it will still continue to have the integrated solver, now you have two approaches to solve the problem. That essentially in Iberian Lynx, that you can build the model from the modeler and export to Nastran and post process in IL. That's what we call flexible licensing schema that's available in IL. And it is powerful tool for automation of your processes with a lot of scripting capabilities and enhancements in Apex. With all these capabilities, we believe that it is prevalent in the aerospace industry, and it will help you to develop your processes very robustly. With that, we believe that it will give you the freedom, the design freedom for you, for your either the current products or the future products to be developed in a manner that you have never seen before. And that's what we believe in Apex IL, that what we are introducing you today. Let's take a look at where we have come from in Apex journey and where are we today. As it has been, Apex will be, next,
Apologies, video.
no problem. Sorry about that. So as it has been, and it will continue to be an easy to use and easy to learn system that is very intuitive with a modern user interface, correct? And it has been the faster CAD to mesh powered with the direct modeling tools, and it is generative in behavior, that which you are all familiar with right from the introduction of Apex. And it is evolved over the period of time to be a CAD to results tools. And with this one, it will provide you the rapid design environment to conduct what if studies. Further, it is revolutionized with the integrated solver built on parts and assembly architecture by providing the complete solution for the linear worlds of simulation. This has been our journey so far. Upon looking at all these capabilities, you repeatedly ask when Apex can support Nastran. We heard you loud and clear. That's when we made a paradigm shift. What is the paradigm shift? The paradigm shift in Apex Iberian Lynx, for it to be Apex to Nastran interoperable, also known as Apex for Nastran, which is a gateway to Nastran. This will open up the whole new horizon for you to explore the possibilities of Nastran with Apex. Let's continue. Let's look at the maturity of Apex since the inception. it is matured over the period of time, as you could see. And Nastran customers' legacy workflow has always been pattern, Nastran pattern. As Apex matured to be a CAD to mesh tool, we positioned it as a companion tool to pattern. That means we could build the model in Apex, mesh the model in Apex, and take the model into pattern. Then we do all the attributes in pattern and export it to Nastran and post-process in pattern. And that's how it was positioned in the early releases of Apex to be it as a companion tool. As CAD to mesh tool becomes more richer and richer to be a preprocessor, then we positioned it as Apex-Nastran pattern workflow, where complete modeling is done in Apex and exported to Nastran, and post-processing still done using pattern. Whereas now the Iberian Lynx is what we call Apex-Nastran interoperability, also known as Apex for Nastran, where complete workflow is supported, including orphan mesh workflow and post-processing with HDFI results. That's what we are today, and that's what you are going to see in essence in the next 45 minutes, the power of Iberian Lynx for Apex-Nastran-Apex workflow. So, as you see here, right from the beginning, we have been adding the Nastran keyword support, and it will continue to add over the period of time. In the early releases, even though we had the few keywords, it was Apex pattern, Nastran pattern workflow, whereas today in Iberian Lynx, we are proposing it to be supporting Apex-Nastran-Apex workflow that encompasses two major ingredients. What are those two things? Number one, supporting the orphan mesh workflow. Number two, processing the results based on HDF5 results that is exported from or generated from Nastran. For those who are not familiar with the word orphan mesh workflow, what does it mean? It means today you can import the Nastran legacy BDF model into Apex. That could be our starting point, and that model will be manipulated, will be modified depending on what the workflow that you would like to do. For example, you would like to create the geometry from the mesh, or you would like to import a part of the geometry into Apex, and you would like to connect that part into the imported Nastran legacy model. So it opens up the world of horizon for you guys to see that you can start from the legacy BDF model, you can merge with the CAD model and build the model completely inside Apex and then export it as Nastran and use Nastran to run the simulation and post-process using the HDF5. That's what is the power of Iberian Lynx, that what we're introducing today. And the future releases of Apex will continue to support the orphan workflow, and our target will be the linear dynamics, meaning where the Nastran is powerful in the industry for doing the linear dynamics, that includes probably frequency response or a transient response or the random response, fatigue analysis, and so on and so forth. And that will be our future Apex. With this one, what we would like to do, we wanted to see how customers perceive Apex Iberian Lynx, for which we thought we could engage with Dr. Steph Evans for him to prepare and position and demonstrate and show you the power of Apex Iberian Lynx. And as Janglan mentioned, he has a wealth of knowledge in the Apex, plus he himself calls as evangelist of Apex, selling, positioning, and promoting Apex for the years. With that one, I would like to turn it over to Steph. Take away, Steph.
Thank you, Vidya. That's a great introduction. Can you hear me okay?
Yes, we can.
Okay, thank you. Yeah, just to follow on what Zhang and Vidya have mentioned, my name is Steph Evans. I run Evotech CAE in the UK, specialising in deployment and training within MSC Apex via our site evotechcae.com. We have 20 years experience in industrial FEA, the majority spent in commercial and military aerospace development. Key thing here is we know your pain. We know the workflows that you've been involved with, and you know the pain points and how difficult things can be with conventional tools. So we've been using Apex for some time, and hopefully we can give an introduction now which will convince you of the benefits of Apex. So with that said, I'll move on with the presentation. So how can Apex improve your productivity? So the release Iberian Lynx opens up your FEA development horizons by becoming your main CAE workhorse. Based on what Vidya said, we now have the Apex-Nastran workflow. Again, Apex can now become implicit in your standard process. So if you're running Nastran as a solver, you don't need to look anywhere else for pre and post capability. Apex with Iberian Lynx and future releases is undergoing continual development, both in terms of generative model build and manipulation, but also in terms of analysis and result exploration. And we'll show some of the key features developed for Iberian Lynx shortly. Apex is built on the Python API, so we have a rich Python-based automation environment, which previously allowed build automation, but with Iberian Lynx we've now got analysis and result exploration support, and this is all enabled through the customizable user-defined tool and GUI functionality, which effectively means that we can customize the creation of forms and what have you to make Apex sit in terms of your discrete company processes or any automation you wish to take care of. The key thing here is that Apex's current and future development is driven by a desire to address key industry pains, allowing you to experience the full benefit of an Apex-focused workflow. You may have seen some of the efficiency gains we've been talking about previously. Hopefully the demo movies we'll look at will drive that home for you. So, working with a number of different suppliers, we've developed a number of aerospace-focused functions or functionality, which I want to take you through now. So first of all, we'll look at the Apex MSC Nastran workflow. So Apex is, or can be now, fundamental to both your current and your future MSC Nastran-based workflow, with far more enhanced MSC Nastran keyword support, both for model import, so reading bulk data or load case entries into your Apex environment, and also exporting that information back out for external MSC Nastran-based analysis. We've also got the ability now to post-process results. So we have HDF5 results interrogation, coupled with Apex's powerful automation capabilities. So you can automate large chunks of your result exploration work. And then we just got a simple infographic here which talks about, or shows rather, the growth of support for the quantity of bulk data file keywords, which are now supported both from an import and an export perspective. So just looking along the x-axis, so we look at coordinate frames, multiple constraints, materials and properties, model definition, and loads and boundary conditions. We've got an exponential growth in the keywords supported by Iberian Lynx over, say, Diamond Python, which was an earlier release from a couple of years ago. And on the right-hand side, we've got a word cloud. What I didn't want to do is bore you with reams and reams of table data, but you can see that there's many keywords supported within the Apex import-export Nastran environment. Okay, so with that said, we're going to have a quick look at a couple of examples. So first of all, we're going to look at an Apex environment with a Nastran deck imported. So we just simply import the deck, pick that from our user base. We can preview the deck. So this allows us to look at things like the keywords, the count of keywords, the unit system, so we can flip from different unit systems if necessary. We've got things like the extent of the model, the properties of loads, and then we can organize the model in different ways. So in this particular example, we're going to organize by contiguous meshed regions, and then simply import the model. The model browser tree is populated with this model information, and then we can look in the tree and dig deep down into the product hierarchy the structure in this case. So each part or sub-assembly is defined as a contiguous mesh region, and then we've got a number of fasteners which tie those parts together. In this example, we've got zero length R-bar connector types, and we can look at the coordinate frames developed for those if we were to use a C-bush or a fastener type explicitly. So bringing the parts back into view, and we can have a look around the model. So the model browser tree, it gives us good visibility and access into the model information. So just clearing up the view and looking in wireframe, we can see we've got typical wing structure, front and rear spar, wing skins, and internal rib definitions. So if we look in detail, we can take out the wing skins from view and show the underlying element topology. So this is typical of a global wing type model where we've got shell elements for webs and beams for stiffeners and flanges. And then one aspect of Apex with the internal solver is that we can start to build up or verify discrete components or discrete sub-assemblies as we work. So in this case, we're just looking at one of those individual rib definitions and then looking at the normal modes response to understand how things are tied together, to look at things like strain energy and what have you. So we can look at typically 6 rigid body modes, and then our 7th plus mode is a flexible body mode, and then we can change the view plot to element strain energy. The key thing here is that we've got control with the embedded internal solver to allow us to verify the model before we look at anything else. And then you can see here we've done this for the full wing structure to show it's tied together as we wish. Changing tack slightly, we can now access results that have been run externally using the MSC Nastran HDF5 file format, reading those results in, and they're ready pretty quickly, and we can see the results are populated, and then we can start to look at our particular result quantity, so a deformed shape in this case, and maybe looking at stresses or element forces, moments, that type of thing. So pretty much any output request you want, we can now handle within the Apex environment for a linear type solution. Okay, so moving on to second example, and now we're going to be looking at some of the orphan mesh behavior that Vidya was mentioning. So we've brought in a bulk data file. There's no associated geometry. We've simply created a volume, shown in the pink square here, to highlight the area of the model we wish to manipulate. So we're going to delete everything else from the database at this stage, and then redefine a local meshed region enclosed within that pink volume, just to give us some target definition for some of the orphan mesh workflow that we're interested in. So again, very powerful now. What we're going to be looking at is a mesh to CAD type operation, which is the inverse of the way industry's been talking, which is CAD to mesh. Obviously with Apex we can go both ways, CAD to mesh and mesh to CAD. So just taking the volume out of view and looking in the model browser tree, we can see we've got 2 discrete sets of entities left, a wing box spar, a rib, and then a couple of wing skins, the upper and lower wing skins. So just showing the wing spar and wing rib, the portion that we're interested in. So we're now going to use some of the orphan mesh tools. So a new feature within Apex Iberian Lynx, we can create faceted surfaces from the mesh to create a geometry object. And you can see on the left-hand side in the model browser tree, we have faceted surfaces within the browser. So we can delete the underlying FEA entities, the mesh, and any associated nodes. And now we can remesh that faceted geometry. One point to say here is that we're looking at flat surfaces. This is equally valid for curved or spherical type surfaces. So we've created the orphan mesh for the spar and wing rib. In terms of the wing cover, or the covers, the upper and lower covers, we're going to take a slightly different approach now. We're going to use some of the other geometry-based tools. So we're going to create a series of curves that pass through the edges of the mesh. We could do this, we could spend a little bit more time tidying this up, but we're basically just picking out the the edges and the sort of mid-curve of this upper and lower wing cover and wing skin. And then once we've got those created, we can look in the model browser tree at the specific part, and we can delete the underlying mesh, and now we'll be left with those bounding curves. So we can now go back into the geometry tools and pick out a new tool for Iberian Lynx, which is the surface loft, which allows us to pick edges and then loft the surface through those curves. Okay, so irrespective of whether they're flat or curved, we can drive those newly created surfaces through. And then once we've got those surfaces, we can now remesh, and we've got our mesh topology in the manner that we might want to carry on with the modelling exercise. So a couple of different ways there of creating remesh geometry using the orthomesh approach and the surface lofting approach. Okay, so moving on to now, we're looking at a typical model aerospace focused workflow. So Apex has the power both implicitly with the standard functionality and also in terms of the automation response or the automation capabilities to look at all aspects of build, solve and result exploration from a aerospace focused workflow perspective. We're going to now look at a Wingbox global local workflow as shown in these images, and this is a standard approach which is used in many supply chains for both commercial and military applications. So we may have a global model, or often called a loads model. So we may have a fairly coarse mesh topology element description of that wing, and we now wish to develop a local detailed model or DFEM for an area of interest. So let's say we wanted to pull out discrete fastener loads or even look at stress raises at features with this technique, but just want to illustrate how Apex can help with this type of workflow. So looking back at this demo, we've got some Wingbox topology, and we zoom in and show that's the topology that we've started off with. So using some of the orthomesh workflows that we've looked at in the previous demo, we've created our faceted surfaces, remeshed, and modified that geometry to suit the local geometry that we may wish to address. Of course, we could couple that with bringing in underlying CAD data, which we have done for a bracket, an interface bracket between the spar and wing rib. But using the standard geometry tools, we've generated the spar flanges, web flanges, and created a series of fastener hard points from our underlying CAD definition. So we've now also got within Apex Iberian Lynx the ability to create custom tools. So we're now using an auto connect fastener tool, which effectively looks for hard points and generates fasteners between paired hard points within a given tolerance. And we can see those fasteners are created very quickly using this tool, and there's a scope for doing much larger models than this in a similar manner to save huge amounts of time. So we can look through that, and we're actually developing bar elements to represent the fastener, but we could change that topology if necessary. So once we've got those fasteners defined, then we can see the markers show the fastener orientations. We now need to tie the detailed region of the model into the global, the original region of the model. And again, there's a number of ways of doing this, but we're just going to illustrate one particular approach. The sort of savvy amongst you may think that this is perhaps too small a region to capture the load transfer across the interface, but again, this is just a demo. We can look at the free edges and show that the coarse and the fine meshes are not connected. But again, using the custom tool palette, we have a pre-written script based on auto tie of nodes. So what this does, it looks for nodes along element free edges and then checks for their positions within a model tolerance, and then generates, in this case, a series of RBE type connections which tie the global mesh to the finer detailed mesh. So typically we could work with a RB2, RB3 or even an R-spline definition to tie those entities together. You can see in the model browser tree we have a very clear and clean way of looking at those discrete tie types, and we can modify them accordingly if necessary, but a very quick way of working with that type of data within the model. So bringing the rest of the model back into view, so we now have our discrete ties or RBE type connections between the detailed and the coarse mesh regions. Obviously we can tie those flanges together. We go from a bar to a shell flange, and just going to a rendered view, we can see the extent of those ties at the interface with the residual structure. We can then run those models and show pretty easily that the GFEM and the DFEM response is largely similar, certainly in terms of wingtip displacement. And then obviously we would look or post-process the detailed region in particular and maybe pull out fastener loads or interface loads between various different components to do our downstream structural integrity checks. Okay, so moving now into solver capabilities. So currently the Apex Iberian Lynx release and the workflow into MSC Nastran supports linear static, Sol 101, normal mode, Sol 103, and linear buckling, Sol 105. The following is one example of a typical workflow. So let's say we have new geometry to build or modify, or even an orphan mesh workflow coupled, which we can now build or manipulate within the Apex modeler environment. The internal solver within Apex via the Apex Structures license allows us to solve that structure. And one thing which is key here is the ability to have incremental verification of a large assembly. So going back to the wing model we just looked at, where we verified one of the ribs and then tied that into a subassembly and then ran the full wing in its entirety. So having the ability to incrementally verify very quickly within the Apex environment is pretty powerful. Once we've got our verified model complete, we can now export our bulk data file definition by exporting that to the MSC Nastran external solver to develop our production level results. And then once they're done, we can generate the HDF5 result and import that back into the Apex model environment for result exploration and post-processing. Okay, so we now have a number of discrete enhancements available within Iberian Lynx, which sit outside of the sort of standard Apex-Nastran workflow, but I just want to run through a couple of those just to give you an idea of the developments that come in with this new release. So first of all, we've got a new geometry tool which allows us to revolve, extrude, sweep and loft geometry, and we can look at this for an engine cowling. So we're going to use the curve shown at the sort of center of the screen now and revolve that round using the revolve tool. So we pick the curve, middle mouse button to accept, then pick one entity which in turn allows us to specify the revolve axis, and we can modify that if necessary. You'll notice that we've got the resultant geometry grayed out on screen, so we can check that that's what we want before we actually create the geometry, and then middle mouse button to accept, and the revolved cowling interface or cowling leading edge is generated, and we can change the color in the viewport as shown. Surface loft, again a powerful technique where we can pick non-coincident edges and then map a surface through those edges, and we can control different tangency controls at the starts and edges and that type of thing. And then a very quick means of building up the geometry for the resultant mesh operation. So next tool we've got is the faceted surface creation, which you saw with some of the earlier workflow examples. So here we've just read in a bulkhead or a rib definition, and we can see the resultant Nastran bulk data file has element topology and a series of shell properties. And what we want to do here is tie in a solid meshed region into this original rib definition. So we're going to delete the shells where we're replacing them with a solid mesh and taking the solid out of view. We can see there's now a hole in the geometry rather than the underlying mesh. And from that mesh, we're now going to use the geometry tool, create faceted surfaces. So pick the single mesh, and Apex will evaluate those surfaces and generate a single set of geometry objects, which we can now delete the mesh from the browser tree, and then remesh that surface using a different element edge length, and we've got the full control of geometry edit tools, so we can now seed an edge, for example, so we can just remesh. And the key thing here is that the faceted surface has remembered the shell element thickness, so we don't need to then repopulate based on the new shells that we've created. So, bringing a solid mesh region into view, we can now simply glue those entities together. We could use a discrete tie, that type of thing, but very quick means of defining topology for that type of model. Okay, so moving on to some of the meshing enhancements within Iberian Lynx. So first of all, we've got some additional hex meshing controls or diagnostic tools. So just looking at a simple solid entity, which we can break up using the standard partitioning tools within Apex, if you're familiar with those, and then 2D mesh. Now you might see here that some of the hex elements are pretty irregular in some of those regions. So what we're going to do now is just a surface mesh with much better control of element quality, and then pick out the regions we want to surface mesh. You'll notice the fillet now turns yellow, which means it's no longer meshable for that single solid. So we've got the hex mesh diagnostic tool, which allows us to see what the problem is, and we can see we've got mismatch in meshed edges. So we just update the mesh seed, and then we can now 2D mesh with appropriate element edge length, and we now have the much better control of element quality in our resultant hex mesh. So very quick to develop that type of structure within Apex. We've also got edge tie enhancements. So again, we're looking at the engine cowling. So we've got a series of shell meshed surfaces which sit in different parts of an assembly. So we don't want to join them together, we want to keep them remote within the assembly. So we shell mesh with a typical edge length, and we can now see we have 3 edges. So we've got no connectivity between those discrete components. And if we put our free edge check on, we can see we've got red lines which illustrate that there's no connectivity whatsoever, and the model would literally just fall apart. So using the edge tie functionality, where we pick the geometric edges and the geometric surfaces, those edge ties are generated very quickly, and we've now got perfect node-to-node connectivity at those interfaces, and we can look at the edge ties on their own within the model browser tree. The key thing for Iberian Lynx is that we can now transform, manipulate our model, and those edge ties are held intact. So we're going to mirror the model about a mirror plane. I'm just using some of the simple model manipulator stuff within Apex, and we can see we've now got edge ties which run across the full transform model, and then a very quick means of analysing the model, and in this case we're using the internal solver to give us the response that we want. We've got some improvements in terms of incremental surface meshing and the controls on shell element XY orientation. I'll just show you that quickly. So we take an example here. So we've got a geometric surface with 4 holes. One of the holes is too close to the edge, and therefore the feature can't be defined in that region. So the incremental surface mesher, which is new for this release, allows us to pinpoint any areas or any features which fall foul of our mesh parameters. So you can see here that edge is shown up in, or rather that hole close to the edge is shown up in red. We can quickly update the mesh parameters and then remesh the whole thing, and we now have a nice ring of washers around, or nice washer elements around every hole. So one more thing we've got here is the ability to control the local X and Y axis direction of a shell element, and this is important in terms of aerospace model definition. Often hand calcs are done on the element results, so we want to have full control over the X orientation. So here we've just changed the shell from X along the long edge to X along the short edge. So a very quick means of doing that. Moving on to the Iberian Lynx Nastran interop capability. So you've seen some of this with some of the earlier demos. We've now got control of ID management, so we can renumber entities very quickly and efficiently. We've got the ability now to import, create, manipulate and export discrete coordinate frames, which we didn't have previously. We've also got the ability to import, create, edit and export discrete ties, which is another way of saying RBE2 and RBE3 type definitions within the Apex environment. And we have a quick video showing that. So we've got a simple lug and tube definition here. So we've got the lug meshed in hex elements, and then the tube meshed in bar elements. and we can look at renumbering. So we're going to renumber the logged elements and nodes from a 10,000 series, and again useful for annotating or discriminating result output. So we can look at our resultant deck, and we can see our elements and nodes start at that 10,000 series, so we've got good control over that. Explicit means of creating coordinate frames. So we've created a cylindrical coordinate system using the standard tool to give us a system which sits at the bore of this hole, and we can renumber that entity at that level if necessary. And we're going to use this cylindrical coordinate frame to specify a radial only, or rather radial constraints on these internal surfaces. So we pick the surfaces and then the reference coordinate frame, and then middle mouse button to accept, and we've done that within the blink of an eye. It's very straightforward to do that type of thing now within Iberian Lynx. Discrete ties, so we can control RBE type definitions. So we're going to use a compliant or RBE3 type definition to tie the bar element to the internal faces of the solid mesh that we've created. And again, on the left hand side, we've got the ability within the model browser tree to modify those outputs very, very quickly and easily. In terms of result post-processing, we can now post-process in a given coordinate system. So because this is a cylindrical system, we can look at R, theta and Z in that output system. We have introduced a new concept altogether now with Iberian Lynx, in that we can now define what we call joints within a model. So previously, pin flag releases or rotation releases, that type of thing, sliding contact within a model was quite difficult to do, or rather relied on lots and lots of entity creation. Now we can do this in a single step. So we've got this shell meshed strut and then a bar meshed secondary struts, and we're going to use a joint. So this is going to be a revolute joint. So we've got lots of different types of joint within the model. So pick the surfaces of the mesh that we want the joint to be attached to, and then a central node or series of entities, and the joint is created, and the display markers show the orientation of that joint, and we can then view that joint in the tree and modify, change the joint type, anything like that, with no problem whatsoever. Okay, and if we look in the resultant BDF file that's generated, we have a series of grids, coordinate frames and RBEs that give us that joint definition. So very, very quick and easy means of defining that type of thing. Result exploration. So obviously with the Apex-Nastran workflow, we've got HDF5 result import. We've got the ability now to probe the model for 0D elements or nodal quantities, and 1D probe to look at results across a path or a point output. And now we've got something which is new to Iberian Lynx, the ability finally to write out those results into CSV format for downstream post-processing in Excel or any other tool that you might wish to use. So looking at this gantry type structure, we've got the Nastran deck written out. You can just double check the deck for the output request, that type of thing. We can run Nastran externally and then develop the Nastran HD5 or HDF5 result format. We can read that by importing those results back into the Nastran environment, import, and then we've got full post-processing or result exploration capability within Apex. So just looking at some of the result displacements, and then looking at one of the booms in particular, which is modelled with 1D elements, we can put the sections on and look at maybe the stresses, so the combined axial or bending stress, or the element forces, the moments, whatever entity we might want to look at. And then we can look at the extreme fiber points, and we're going to use the probe tool to pull out the combined axial and bending stresses at those given points, which writes them to a table, which we can look at or manipulate, whatever we want to do, sort, and then write that as a CSV file, and we've got the data available for external post-processing. And again, all of this result exploration stuff is now opened up in terms of the Python automation environment. Okay, and saying that, we're moving on to some of the customization and automation tools we've got. So scripting is now available, as I've just said, for analysis and result exploration. We've got the ability to create custom tools, and a quick video just to show this is a simple macro that we're running, but we parameterize some of the inputs, and this allows us to run a full model build, solver, and result exploration process, effectively black boxing this from the user. So it could be useful for engineers with less experience, or if you want to lock up the workflow. And that basically runs through the build, solve, and output. In this case, we're looking at a buckling response for a simple panel. So almost negating the need for hand calc if you wanted to do something slightly more exotic. And we can look in the post-process output for this buckle panel, look at the different modes, and then see that we could potentially have a design problem in that we have a couple of modes where the load factor is greater, or the buckling factor is greater than 1, shown in red in that region. A second approach, now this is going to be looking at the custom tool development. So we might have a need to build a parametric series of geometries. So in this case, we're looking at a flexible tube. So we go into the custom tool palette, pick the particular function, and then input the geometry, the thicknesses, the materials, and what have you required for this parametric study. Run the script from the form. So that, again, there's no interfacing with the script once this is built, and we can see how the geometry is manipulated or generated, and then meshed to our requirements, and we can build in element quality checks into that if necessary, and then we can just simply run the analysis and understand what the model response is going to be. And again, it's a very quick way of developing that type of thing through the Apex scripting environment. Okay, so a final slide here. The key thing with this is that Apex is now a real game changer in terms of your aerospace-focused FEA workflow, albeit with Apex on its own, or in terms of Apex and Nastran capabilities coupled. The key tenets of Apex are that it's still very, very easy to use and equally easy to learn. We can see a 10x or huge efficiency gains with Apex by coupling the generative direct modeling nature of the environment and Python automation. And now Apex is key to your Nastran workflow, opening up your Apex universe.